Okay. So thank you very much for coming, and it's a pleasure for me to introduce Dr. Dan Adams. Dan did his PhD at the Colorado School of Mines and then joined JILA as a postdoctoral fellow in 2010, and since then he's become a senior research associate. And Dan has really done amazing things with the imaging group, starting off developing coherent imaging initially as a sort of an interesting imaging tool, to now where it looks like it can do things that cannot be done using other approaches for imaging. And so it's my pleasure to ask Dan to present his work.
Well, thank you, Margaret. I appreciate the introduction, and that's exactly what I'm going to be talking about today. I want to share with you, very excited to be here, to share with you something that I consider a paradigm shift in the field of microscopy. This has come from a revolution in the way we think about doing microscopy over the last 10 years. Specifically, I'm going to be talking about doing X-ray imaging at the wavelength limit, but really harnessing the power of coherent X-rays to accomplish this. Okay? So I'm going to bring you through a brief introduction about what I do here at JILA called Coherent Diffractive Imaging, show you what that's about, and then that will lead into some advances that we've made in full field X-ray microscopy. And the basic idea here is that we want to move toward a position where we have these X-ray microscopes possibly sitting on a tabletop, just like you'd see an SEM or an AFM. Then I'll leave off with a little bit of perspective about where the field is going and how we're going to take it there. Okay. So what I'd like to do is start off with the basic idea that if you are looking at something, a phenomenon, on a specific length scale, you need a probe or another phenomenon that exists on the same length scale to get information out of that system. So what I've done here is I've plotted just some things on different length scales, from the macroscopic down to the cellular level, and then down into the nano world. There's a lot of interesting phenomena that we want to look at in the nano world. And what you can do is write down the uncertainty relationship, and from that derive immediately an expression that says that for an ordinary microscope, the best resolution that you can hope to get is related directly to the wavelength. What I like to do is take that a step farther and just use kind of a little example here about derive an expression that states that the minimum spot size that you can get for a field is related also to the wavelength. So what I'm doing here is I'm taking a Gaussian beam, just in this illustration, and I'm focusing it down, and then all I'm doing is shifting the wavelength from the infrared to the X-ray region. And what you can see is that the beam size also follows this scaling. Okay? And the point here is that it turns out that coherent X-rays are actually an ideal probe in the nano world for a variety of reasons, other than the fact that they exist on the same spatial scale as the phenomena that we want to look at. They can penetrate thick objects, opaque in some cases, visibly opaque objects. And we have this beautiful elemental and chemical specificity that are associated with certain regions of the spectrum. Some of our spectra overlap with these atomic absorption edges, so we get this built-in absorption contrast mechanism. We can image small features in 3D at the wavelength limit. Okay, that's what I'm going to be talking about today, using the power of coherent X-rays to do three-dimensional imaging on the nanometer scale. And due to the way that we make these X-rays here at JILA, they come out in the form of very short pulses, so we can do all of this on a very fast time scale. Okay? So just to say again, the idea is to have this X-ray microscope that can look at the nano world, look through visibly opaque objects, and capture all dynamics that are relevant to function. Okay? So you may ask yourself, how would an X-ray microscope then stack up with some other microscopy techniques that we do know? Okay? So we know in 2014 that a Nobel Prize was awarded to some of these scanning stochastic methods like STORM, and now we're even using methods called like IPalm. This is interferometric palm. Using these techniques, you get exquisite transverse resolution, even down to 10 nanometers and below. However, you need to know a lot about the sample before you put it in the microscope. They rely on these sparsely emitting fluorophores that you tag on biological samples. So you need to know, one, that the sample can accept this fluorophore, and also that it's visibly transparent. So that brings up a question: what do you do if the object that you want to image is actually visibly opaque? So on the electron side of things, we are now living in a time when we can visualize individual atoms in a mesoscale size object. Okay? So these are some examples of looking at individual atoms. Here's a nanocrystal of platinum. We can look at the atoms in this nanometer scale object. It's an amazing time to be alive. What an amazing tool. Of course, a lot of these techniques are based on models, And they need a lot of extensive sample preparation because you need to make the sample very thin to get the electrons to actually go through it. On the X-ray microscopy side of things, we're already imaging nanoparticles. This is some nano gold spheres on a silicon nitride membrane. We're doing biological imaging, and in certain geometries, we can even get atomic scale resolution. For full field scanning or non-scanning microscopy, we have a 2 nanometer resolution limit for X-ray microscopes. We're pushing that down even farther now. Like I said, it's a non-scanning technique. We get this nice chemical map that we build up. And you need to actually know very little information about the sample before you put it in the microscope. It's non-invasive, and it turns out that you only run into dosage limitations in biological systems. Okay, so if you're looking at material systems, we don't run into this limitation that's set by how much exposure that the sample can take. So then the question comes up, why don't we have these X-ray microscopes everywhere? Why aren't they all over the place in the scientific community? Well, the answer is that it's actually very difficult to build an X-ray lens. Okay, so the materials that we could use to build X-ray lenses can't bend the light, the indexes are too close to 1, or they're very absorbing. But what you can do is build a diffraction lens. This is a Fresnel zone plate, and the basic idea is that if you have a plane wave incident on a pinhole in the far field, you get your area disk. What you can do is design a series of concentric rings to engineer that spot to be very bright in the far field. Okay? And then this object acts just like a regular lens. This is full field zone plate microscopy. The idea is that you take this zone plate lens, you smash it up against the sample as close as you can, you make a magnified image of your object in amplitude. The best zone plates in the world right now can get you down to about 10 nanometer resolution. That's only at more or less one place. For the rest of us, we're stuck at about 25 nanometer resolution using incoherent X-rays, okay, with this zone plate. Another form of this zone plate microscopy comes in scanning transmission X-ray microscopy. And this uses the idea that I presented earlier. You take an incoherent source of X-rays, you focus them down as tightly as you can, which is again related to the wavelength. You scan your object, and in the far field you integrate, you build up an absorption map of the object. But what I want to point out here is that it turns out that the resolution of both of these techniques is actually not limited just by the wavelength. It turns out that it's limited by the fabrication quality of these zone plates. Okay? So what I'm proposing right now to you is, what if we could harness the coherence properties of X-rays, coherent light, to do something more than absorption contrast Fresnel zone plate imaging. Okay? And this is called coherent diffractive imaging. The field was started in 1952 by a man named David Sayer. And you probably can't read this from where you're sitting, but I like to put this up because this is actually the entire paper that started the field of coherent diffractive imaging today. It was written in 1952. And basically what it says is that if you're doing Bragg diffraction, the phase problem is not well defined. You actually can't get the phase of the light that exited the crystal. So you can't learn more about the crystal. But if you could somehow measure light in between the Bragg peaks, David Sayer says, you might have a chance of reconstructing the field that left the crystal and get a lot more information from that experiment. And luckily, he left us off a little bit of perspective at the end of this article, and he said the extension to 3 dimensions is obvious, so we know exactly where to go from 1952 to now. In all seriousness, we have made a lot of progress actually in doing 3-dimensional X-ray microscopy. In 1980, he wrote another article where he put one paragraph in explaining in a little bit more detail his idea about CDI. But it wasn't in fact until 1999 that John Knapp took this sample, which was just holes poked in a gold foil, to a synchrotron. He allowed this coherent source of X-rays to hit the sample and then propagate to the far field. And we know that the far field pattern, this interference pattern, is related to the sample by a Fourier transform, but only if you know the full wave. So we're missing half of the information here. We're missing the phase. And so we have to enter this 2-dimensional phase retrieval game. Okay, and so the way that coherent diffractive imaging works is you have a plane wave. It's incident on an isolated object. So this object is actually surrounded by zeros, okay, in this geometry. The wave diffracts through the object and then in free space to the detector, where we collect it in intensity. This is a nonlinear operation. Okay? And so we have to get the phase to numerically backpropagate this to the sample to form what is considered to be an image of the object. Okay? And how does that work? Well, this is the 2-dimensional phase retrieval algorithm. Okay? And we start off with a guess that's embedded in a 2-dimensional Hilbert space of square integrable functions. and we simply do proper mathematical projections of that guess onto two constraint sets. Okay? These iterative projections bring our guess ever closer to the intersection of these two constraint sets, where we hope to find an object that is consistent with both constraint sets. In coherent diffractive imaging, the two constraint sets are, one, the modulus constraint, which is the data that we took. Okay? That will be consistent with all diffraction imaging techniques. And we also have a real space constraint. It turns out that that is also very similar for all techniques. The real space constraint turns out to be related to the modulus constraint in as much as we make sure we can Nyquist sample the diffraction pattern. And what that leads to is that the object is, in a sense, band limited. It's isolated. So the fact that there's no scattering outside of a certain radius of this object gives us enough of a constraint to solve the two-dimensional phase retrieval problem and get an image of this object back. How does it work in practice? We take our diffraction pattern, okay, take the square root, assign a random phase to each pixel, and then Fourier transform. Now, the algorithm thinks it knows the object, but of course the phase that we gave it was rubbish, so it has no idea what the object is. But what we do know is that we Nyquist sampled this diffraction pattern in intensity so that the object, the amplitude, is now surrounded by a bunch of zeros. So we can simply multiply by a mathematical support that insists that the object has no scatterers outside of this radius. Okay? Then we inverse Fourier transform. Now the algorithm thinks it knows both the diffracted amplitudes and the diffracted phases. Of course it knows neither, because we're on iteration 2. But what we do know is the diffraction intensity that we measured. So we can replace the amplitude that the algorithm thinks it knows is right with the correct one, and then keep iterating by replacing the amplitude in the Fourier domain and multiplying by a support in the object domain until the algorithm both finds an object that fits inside of this support and made the diffraction that we measured. Okay? And it turns out that for the most part, this phase retrieval algorithm that also gets the image is unique. Okay, and I want to say a word just quickly, kind of sketching out the process of what we call oversampling the amplitude of the diffraction pattern, or Nyquist sampling the intensity of the diffraction pattern, and how that leads to the support constraint. If we look at a signal, let's say it's a rectangular function, it fills up the entire grid, but I plotted out a little bit more so you can see what's going on. We take a Fourier transform to get to diffraction space. We got our sink, and I plotted a sinusoid of the same frequency, and we've Nyquist sampled this sinusoid. Okay, so we get our two samples per period. But it turns out that we actually don't measure the amplitude. We measure the intensity. This is a nonlinear operation that essentially doubles the frequency of the signal. Okay, so now this signal is not sampled properly, okay? So it cannot be reconstructed from its samples. But if we Nyquist sample the intensity, we look back at what that does to the amplitude. Now the amplitude is oversampled. And if we look back one step further to the object, we can see that the object is now surrounded by zeros. We work kind of backwards in the microscope, where we insist that the object is surrounded by zeros, which allows us to Nyquist sample the diffraction intensity. And in this way, we can now get an image of the diffracting object using coherent X-rays and bypass the need to use this aberrated, very lossy Fresnel zone plate. Okay? So it turns out that the Fresnel zone plates are actually quite lossy. You're going to get about 3% of the light through this. And also, coherent diffractive imaging is one of the most photon-efficient imaging methods around. We actually use all the photons that get to the camera, okay, that diffract through this object. So using this idea now, we can really envision a microscope based on coherent diffractive imaging. And there's some added benefits that come with using coherent diffractive imaging. There's no aberrations, like I said. We can really get down to the diffraction limit that's limited now by the wavelength and the NA of collection, and not limited by the aberrations in the optic. We can image through thick samples. Again, we can use the penetrating power of X-rays to look through samples. We can even look at buried samples, right? So here's a little cartoon of some silicon features buried beneath some metallic layers. A visible laser would bounce right off the top, but an X-ray source would go through here. We'd get our diffraction and be able to reconstruct an image of the diffracting features. Again, we get this nice elemental contrast of the X-rays. But what I like to point out here is that because we have to get the phase, we actually do get the phase. Okay? This is necessarily and uniquely a simultaneous phase and amplitude contrast imaging technique. Okay? So that's very powerful. And I'll show you how the phase contrast comes into play in just a little bit. As the name implies, we need a coherent beam of light. And in most cases, we need an isolated sample. So when I first started working on this, microscope, I knew immediately that we had to make it general. We needed to stop tailoring the sample to fit in our microscope, and we needed to start tailoring the microscope to accept any sample. Okay, so what I'm going to talk about in the upcoming slides here is how we alleviated this isolation constraint. And on the road to figuring out how to do that, we developed, co-developed, and found very advanced techniques. We found that we actually don't even need a fully coherent beam of light. Okay, so we can deal with sources of decoherence in our beam. There's many of them: spectral, spatial, polarization. And I'll tell you about two. So that's an overview of coherent diffractive imaging and using the power of coherent X-rays to do this type of microscopy. So you might think to yourself, well, how do you get coherent X-rays? So what I've done is I've shown here some of the sources that we can use that give coherent X-rays. On the left are facility scale sources, and on the right are tabletop sources. Now this is a synchrotron and an XFEL here. These are amazing sources. They put out an incredible amount of flux, average power and peak power. And for some experiments, this is what we have to use. We need that type of flux to get the resolution that we want. On the tabletop sources, we have these EUV lasers, which are quite nice, but they're kind of stuck around this wavelength. It's very hard to go below that. The scaling to go to shorter wavelengths is very unfavorable with respect to power. What I'll be talking about today is how, in fact, the high harmonic source turns out to be almost a perfect source for coherent diffractive imaging. Okay. One other thing before I move on, I want to just say real quick. So these are very large sources. You can play games with a synchrotron called slicing to get some temporal resolution. You can get down to about 100 femtoseconds, but the jitter is in fact so bad that it's not really that usable at the current time. Free electron lasers suffer from the same kind of jitter, and of course they are very large and very expensive. Due to the nature of the high harmonic process, we inherently get pulses that are on the order of 10 femtoseconds in width, and it's a very compact source, so that makes it very attractive. Another thing that's very nice about the high harmonic source is that we can tune the output wavelength by simply tuning the input wavelength to our high harmonic generation source. Okay, so that's very nice, and this is just kind of a plot showing the nice spatial coherence that's built into the source. We don't have to do anything to make this spatially coherent. Okay, so that's an overview of coherent diffractive imaging and why we want to use X-rays to do it. Using this concept of an isolated sample, we stuck this sample into our microscope. It looks like this. I'll explain in just a second. This is some holes poked in a gold substrate. We were able to set a world record for 22 nanometer resolution. That's the best resolution that has ever been attained on a tabletop using any light-based microscope. So that was a quite nice achievement. And this is a typical geometric arrangement of our microscope. The wavelength that we will be working at will be in the corner of one of the pictures on every slide. We take an infrared driver, we focus it into a hollow capillary where we backfill it with a noble gas. The intensity of the field is so high that it rips an electron off of an atom. The electron accelerates in the field, gets turned around and then recombined with its parent ion, and it loses any excess kinetic energy that it gained in that process in the form of a high energy photon. That mixed with phase matching of the fundamental with the X-ray gives us our bright, spatially coherent source. Now, it turns out that this process is not incredibly efficient, so we have to filter off some of the fundamental in a two-step process. First, we shine both beams off of a silicon plate that's set at Brewster's angle for the fundamental. A lot of the fundamental is absorbed in the silicon, and the X-rays bounce off of it, and any residual light that's left over from the fundamental is reflected by thin metal filters. And one thing that's important to know, and it'll come back in just a minute, is that by virtue of the high harmonic process, we actually phase match a bundle of harmonics, about 5. But the coherent diffractive imaging algorithms, when they were first written, assumed that the beam was monochromatic. So what we did is we shined these off of some Bragg reflectors, these multi-layer mirrors that are designed to have very narrow bandpass, and we select out one harmonic that we shine on our sample, collect our diffraction pattern in the far field, and then run phase retrieval. And again, we got this really nice 22 nanometer result. But it was time after we achieved this to move on to more advanced techniques because we wanted to kind of overcome this sample isolation constraint. So what we did is we collaborated with some of our partners, and we adapted a technique called keyhole coherent diffractive imaging here to work on a tabletop. Okay? The way that keyhole coherent diffractive imaging works is that it insists, instead of the sample being isolated, we move that requirement from the sample to the microscope. Okay? We simply make a hard edge on our beam, and in this way we can kind of, in a cookie cutter style fashion, image different parts of the sample by insisting that the beam now has a hard edge on it. In synchrotron facilities, the way this works is that they focus the light very tightly with the Fresnel zone plate. The Fresnel zone plate also puts a hard edge on the beam. You put the sample slightly outside of the focus, and if you look at the geometric optics, what you get is a hard edge on the beam there. Okay? And this gives you your isolation constraint. It turns out that if you stare at this image long enough, it looks a lot like inline holography. And it turns out that that's exactly what it is. This is a form of Gabor holography, so I want you to look in the data sets, the raw data coming up on the next few slides, for a low resolution version of the object in the DC part. Now, one thing to note about keyhole coherent diffractive imaging is that it does require full knowledge of the input beam. So we've taken a lot of the requirements from the object and instead put them into the microscope. So you have to know everything about the input beam. So now we have a two-step phase retrieval process. The first step is to characterize the beam. The second step, after you know the beam, is to get the sample. And using this technique, if you know the phase, which you get from this, you can map that directly to sample thickness if you know the materials. And so we did, and we compared this to an AFM of the same sample. This was now holes potent chromium, very much like our previous sample. But it turns out that chromium at 30 nanometers is quite transparent, so if the beam didn't have a hard edge on it, the beam itself would have spoiled our isolation constraint. Okay? So we can see that between AFM and CDI, we get very nice agreement of the depth of the features. But what I like to point out here is that this very small feature, this 50 nanometer feature, actually was not drilled all the way through the sample. And if we had put this sample into the microscope, the SEM, upside down, we actually would never have seen that feature. Okay, but using the penetrating powers of the X-rays, we're able to see through this object, and no matter how we put it in the microscope, we get a good reconstruction of this feature. So that's very nice. Using this technique, we just wanted to show that we can actually do extended samples. Here's some gold, and we scribed some features in it. Blue goes with the blue reconstruction, and red goes with red. And this is basically to show that we're able to do real extended samples. The beam does have a support constraint built into it now. And now the microscope in transmission is very general. Okay, but we wanted to take this one step farther. We wanted to look at objects that were too thick even to get X-rays through them, or maybe even study surface dynamics like surface acoustic waves, or things like that. And so we wanted to push this technique to allow us to do imaging and reflection, and it turns out that that was actually a very difficult problem. If you remember back, it wasn't until 1999 that John Now took a sample to a synchrotron and did CDI for the first time in 2D. But it wasn't until 2011, in fact, that people were able to do reflection mode coherent diffractive imaging with X-rays. Okay? This group did a pretty nice job. Their wavelength is actually quite small, but the resolution isn't so good. And the reason is they simply transposed the reflection problem into a transmission problem. They put a very small aperture after the reflection sample, reconstructed the wave inside of that aperture, and then back propagated the sample. And this necessarily limits your NA, and the resolution suffered a bit from it. A good first effort. These guys went to a synchrotron. They machined some samples, this is an SEM, onto a multi-layer mirror that was specifically designed to be highly reflective for that particular color. And they were at basically 0 degree incidence. So they didn't have to deal with any off-axis or high NA diffraction physics to solve this problem. Good result, but not super general. These guys are at very high photon energy. And to get any reflectance, they had to go at very glancing incidence, which means that the beams spread out a lot on their sample. And so they designed this sample to go inside their microscope, very long in one dimension, very skinny in the other dimension. And then they ended up doing tomography anyway. So it turns out that this is actually the only other high harmonic generation reflection mode imaging result. Here's an optical image of the sample. It's a good first try. For these guys. It was low NA and very low angle, so they didn't have to deal with high NA or off-axis diffraction physics either. But what I like to do is show this slide and then show our first crack at reflection mode imaging. This is using an advanced technique, even more advanced than keyhole, called typography. I'll explain how that works next, but it is a convolution type technique. Here's the high harmonic beam that we use. We basically scan that across the sample, take multiple diffraction patterns, and then using a lot of information, we're able to get high fidelity images of this sample, which is now titanium features on a silicon substrate. Here's our CDI reconstruction. It's a complex image. The hue represents the phase, and the brightness that you see there is the reflectance of the sample. Again, we're in this really tightly focused geometry, okay? And so you can see this low resolution image of the object in the raw data. Okay, so if you're in vacuum and you're kind of cruising around on the sample, it's actually hard to know where you are. But this constitutes what I like to call a microscope in a microscope. Okay, so we can zoom around on the sample, find what we want to image, and then take a high resolution image of that object. Okay, like I said before, this new technique called typography is more or less a blind deconvolution algorithm. From it, you get your object and your beam, but it does require multiple diffraction patterns. Now, keyhole coherent diffractive imaging, if you know the beam, only requires one diffraction pattern, so it lends itself to dynamic studies. So you can get the beam from typography from this blind deconvolution algorithm using many diffraction patterns, and then plug that into the keyhole coherent diffractive imaging technique. So we have a lot of different techniques that we can use to do this imaging now. This is the way the typography works. We still have the two constraints from before. We have the diffraction data we took, and the beam is oversampled, so it has a hard edge on it. But we add a third constraint now, and that is we take multiple diffraction patterns, we scan this isolated beam across the sample, and we simply ensure that there's a lot of overlap between different scan positions. So what that means is that in adjacent scan positions, the reconstruction has to be identical. Okay? This particular data set, we collected 100 different diffraction patterns. Okay? That's a testament to the stability of the high harmonic source. So we have enough flux to do these experiments. And it's stable enough to do typography. So one other thing that typography does is it looks for a high harmonic beam that's consistent with all of the scan positions when it's reconstructing this object. So the beam can't change, or it actually ruins your reconstruction. So this is a testament to the stability of the high harmonic source. This is quite nice. One last thing that I'll point out here is that in reflection, it turns out that the phase information that you get maps directly to height. So now we're doing three-dimensional imaging with X-rays on the nanometer scale. We wanted to see how good our high resolution was, so we took an AFM of this sample, we plotted a histogram of the heights, and we found that they matched to better than a nanometer, okay? So one tricky thing that we had to take into account was the Fresnel phase that you get off of reflection from these different samples, okay? And we actually even had to take into account the Fresnel phase that you get from the oxide layers to get this exactly right. But when we did that, we were sure that we were getting better than sub-nanometer precision in our axial direction. But we wanted to see just how good of an image we could get in reflection. So we increased the NA, and we redid the exposures on a similar sample with a lot of texture on the surface now. So this is our high-resolution reflection mode result. Okay, here's the amplitude of the reconstruction, here's the phase, and here's an SEM for comparison. This was 200 scan positions, so we definitely have a very stable source. About 1/10 of a second of exposure time per position, which means that a total exposure time of about a minute. We took three accumulations per position. But it turns out, in fact, now we are not limited by the flux from our coherent EUV source. We're limited by the readout time of our electronics. Okay, so we're partnering with some collaborators to try to kind of solve that issue. We get better than 40 nanometer transverse resolution, and I'll show you on the next slide how we can justify this 5 angstrom axial precision. It's very high contrast. I'll show you this little video while I tell you. This is the typographic reconstruction algorithm. These are sub-iterations. Now you're looking at full iterations. And it turns out that this is an incredibly powerful algorithm. If you know the input beam, it will get the object within 10 iterations. So it's a very, very fast, powerful algorithm. One thing that's nice to look at is that the contrast mechanism in CDI is quite nice. So if we look at this area of the sample, and then we look at the SEM, you can't even really make out the same features here, but they're very visible here. So just due to the contrast mechanism in coherent diffractive imaging, we get very good looking images. Now I want you to think about the difference between this technique and keyhole. So keyhole, you have one diffraction pattern. All of the other techniques, you have one diffraction pattern. Typography uses multiple diffraction patterns. So we had 200 diffraction patterns for this data set, as opposed to one. So that leaves us with a lot of redundant information. And using that redundant information, we can do a lot of different things. One of them is to correct for systematic errors in the scanning stages, and I'll show you that in a second. So getting back to kind of looking at the height precision of this measurement, we wanted to look at a region of the sample that we didn't have to worry about the Fresnel phases. So we could just look at relative height differences. So we looked at this region right here. It was homogeneous in material. And we looked at our CDI reconstruction and an AFM of the same area. Okay. For reference here, we have this line out. This is the raw reconstruction versus the AFM. And if we plotted a histogram of the differences between these two, we can see that the width of this histogram distribution is about 4.3 angstroms. That's half width. Okay? But then we realized, oh, we actually don't even expect the same transverse resolution from CDI as we do from AFM in this case. Because one of the hard parts about CDI is that you need very high dynamic range. So if you have weakly scattering objects next to very brightly scattering objects, it's hard to reconstruct that with high fidelity. And so we decided to try to compare apples to apples better. And so we took a histogram of the AFM heights and just threw out everything that was outside of these trench-like features. We redid the difference histogram between these regions where there was non-zero data. And we got a histogram width of about 3.7 angstroms. And then we thought, oh, why don't we just design a point spread function that's representative of our CDI microscope, apply it to the AFM, and then optimize its width based on the error between these two. And you can see that these two, this is a point spread function that's been convolved with the AFM. These two match much better. We take a difference histogram, and now the full width, 95% confidence interval of this distribution is about 6.4 angstroms. So we've shown that we do have sub-nanometer resolution in the Z direction. This is from typography. Using typography, like I was talking about before, you can solve for a lot of other things besides just an image of the object. So what I've done here is I've made a little simulation. Here's the beam that I'm giving it now. And like I said before, it should get the object reconstruction in about 10 iterations. This is going to be a woman's face and some bumpiness for the face just to make it hard. And as an input to the typographic algorithm, what you give it is the diffraction patterns and where you measured them. Okay, the positions of the stages. The green pluses is where I did the simulation. And the red X's are where I told the reconstruction algorithm that I did the simulation. And there's basically no correspondence here, I just added randomness. I'm going to let this play through a couple times. On iteration 25, I want you to watch as I allow the algorithm to solve for the errors in the positions. Watch those red X's hunt for those green plus signs. So it's simultaneously solving for an image of the object that has phase and any errors that you have in the scanning stage positions. So if you have thermal drift, it can correct for that. I'm going to let this play through one more time, and what I want you to watch this time is the reconstruction. It should have it in 10 iterations, but because the positions are so bad, it can't get it. But after iteration 25, watch how quickly you start to see features of this eye. And not very many iterations later, you see the full reconstruction, the error plummets. And this technique is very powerful. One other thing that it can do, which is quite amazing, this was very surprising actually, is that there's enough redundant information that we can actually now deal with sources of decoherence in our beam. So one source of decoherence is spectral decoherence. Okay? And if you have multiple wavelengths that are shining on the sample simultaneously, it turns out that typography can rip apart that diffraction pattern that's composed of an intensity average over the wavelengths and get a diffraction pattern for each of the colors and make a reconstruction of the object for each color also. So the high harmonic source naturally basically phase matches about 5 harmonics. We can shine them all simultaneously onto the sample, collect an intensity average diffraction pattern, and use typography to get an image of each one of these objects for each color. So that is a very powerful microscopy now. We can do real hyperspectral or imaging spectroscopy now. Okay, that's a great tool to have. One other thing I will mention is that there's a lot of different geometries that are associated with coherent diffractive imaging. This is called Bragg CDI, and what you do here is you take a crystalline type sample, this is a nanopillar, and you do Bragg diffraction off of it. And because it's imperfect, you get some scattering outside of this, what should be a delta function. And then you simply rotate the object a little bit and basically do Bragg tomography, and you can reconstruct a 3D image of this sample. And now the phase corresponds to quantitative stress and strain maps. Okay? They did this again for a little nanoparticle in an operating coin cell, and you get quantitative stress and strain maps here. They were at 10 keV, so this can actually be in air. And this device was operating when they looked at it. So that's very powerful. Okay, so now I've walked you through some of the advances that we had to go through to make this a general full field microscopy. And I want to leave you with some perspective on where the field is going, okay? Where we want to take this field and how we're going to do that. The first thing we want to do is really get ultra-high spatial resolution, okay? We want to definitely go down past 10 nanometers. And we want to even try to get sub-wavelength resolution, okay? And I'll talk about that in a minute. But again, what we'll be doing is changing the input wavelength so that the output wavelength goes all the way down, even past a nanometer, so that we can get ultra-high spatial resolution, something that the other techniques just can't do in the same scenarios that we can. Instead of doing this, possibly one other solution to this problem is to use these microfocus X-ray tubes. Okay? They're more or less incoherent. So the question arises, how do you make this essentially an X-ray light bulb? How do you make it coherent? There's several different sources of decoherence. Spatially, it has to be coherent. You have to have spectral coherence and we have to have one polarization. Well, it turns out that you might be able to use Bragg diffraction to do all of this. You can use these so-called doubly curved crystals, coat them on to a curved optic, and point the Bragg diffraction peak in the same direction as the focusing. Out of this, you get a very highly monochromatic beam just because of the Bragg diffraction. You can use it to spatially filter the beam to get your spatial coherence, and in the right geometry, you might even be able to use it to filter the polarization. Now, it turns out this is the spectrum of this source, and there's a lot of energy integrated underneath this tail. So if we could just capture a slice of this 10 keV peak, we'd be good. But it's important to note here that these sources put out 75 watts of X-ray light. So we have a lot to work with. If we filter out the coherent part, we may have enough 10 keV light to do microscopy on a tabletop like this. We definitely want to do 3-dimensional imaging. This is kind of us pushing the limits of what we can do on a tabletop. We're already doing this kind of 2+1 hyperspectral imaging in reflection. We want to do buried layers, but there's nothing wrong with doing tomography on a tabletop also, so we'll be pursuing that. And as I see it, there's two great potentials of tabletop coherent diffractive imaging. One is, like I said, looking through objects that no other techniques can look through. The other is utilizing the very short pulse nature of these X-rays that we make here at JILA to get very high temporal resolution. And it's the same story as before. If there's a phenomenon that exists on a particular time scale that you want to look at, you have to have a probe that exists on the same time scale. Okay? So you can derive a similar expression using the uncertainty principle, and what I did is I translated that into wavelength now. We have a constant bandwidth, a transform limited pulse, and all I'm doing is shifting the wavelength, and as I do, you can see that this pulse gets shorter and shorter. So being in the X-ray range gives us really short wavelength probes to look at very small features and very fast features. So it turns out that this high harmonic generation process is perfect for coherent diffractive imaging. The way to put this in context with the rest of the talk is to plot length on this axis and time on this axis. It turns out that there's a lot of phenomena that we want to look at that exist on a nanometer scale but are also incredibly fast. But there's not a lot of sources that can look at that. Okay? But these coherent X-rays that we make here at JILA are perfect for that. So what we want to do is, we've already shown that we can make high harmonics with about 1 nanometer wavelength. If you Fourier transform this spectrum, it gets you about 2.5 attosecond temporal resolution. Okay? We're already in the water window. We might do biological imaging, but we've also shown that by just using the high harmonic process itself, we can get isolated attosecond pulses out of this. Okay? So we have all the temporal resolution that we need to look at a variety of phenomena. Okay? And the first thing we're going to do is try to answer some of these questions that arise when you shrink systems down to the nanoscale. There's a lot of questions that come up about thermal dissipation on the nanoscale. The models are not well refined for that length scale. So what we're going to do is put, for instance, titanium features on a substrate, shine a strong pump pulse on them, heat them up, and watch them oscillate and cool down. And maybe we'll be able to answer some of these questions. This is an imaging end station. We have a pump line coming here and a probe line coming here. So we're just about ready to start doing these dynamic investigations. You might also consider using this built-in contrast mechanism that I was talking about. Here's the magnetic M edges. Okay? So we already have a contrast mechanism to look at, possibly think about looking at these magnetic domain structures. Okay? We can heat these up and then look at them cool down and do magnetic domain imaging, investigate things like spin transport, ultrafast demagnetization events, and things like that. So finally here, what are some of the fundamental limits associated with coherent diffractive imaging? Okay, what do we have to actually overcome to really get down to the root of what the fundamental limits are? So we want to go the highest spatial resolution possible. We want to get possibly sub-diffraction limited imaging, sub-wavelength imaging possibly, okay? So you might think that sounds crazy, but kind of taking some advice from these fluorophore type imaging techniques, here's a fluorescence image alongside a CDI image of this sample, and you can see the chemical map. Each one of these tiles represents a different chemical element. And so we may think about scattering very small nanoprobes onto the sample and doing this fluorescence type stochastic imaging also. We'll always be limited by shot-to-shot noise and just regular Poisson noise here. But we might think about even CEP stabilizing our lasers to beat down some of this spatial noise and also maybe some of the temporal noise. We definitely need to go to 3D. We want to do 3D imaging of mesoscale objects. Look at thick samples that have multiple scattering. This is outside of the Born approximation now. So we have to develop new techniques to handle this type of physics. And this, of course, brings up a really large problem. This is the big data problem. So we can easily generate terabytes of data in one day. Okay? And so one possible solution is to have an active transfer node to send the data to a very large processing center like NERSC, have them do the processing and then send the image back. We might also think about doing onboard processing, throw out the data that we don't need, keep the data that we do need, and get our images that way in an efficient way. We want to utilize the high temporal resolution of these sources, do functional imaging of thick samples. And of course, we can do CEP stabilization there to lower the noise also. And this brings up the idea that there's great prospects for collaboration between people even here at JILA and NIST to do some of these things. We're going to need some funding for that. Here's the funding landscape that we're operating under right now. We just came off of a very large NSF ERC. We work a lot with DoD. We're being funded heavily right now by DARPA. The first grant I ever wrote was a $1 million STTR with KM Labs and the Air Force. It turns out that we actually don't have to go looking for applications for this microscope. People are trying to get their samples into our microscope, and one of those people are the semiconductor industry. The SRC, I'm managing a grant with them. This is the Semiconductor Research Corporation. They're very interested in the technology. We got past the pre-proposal stage for an STC. We have a NERT in process, and we're going to be keeping our collaborations with the semiconductor industry very tight, and of course, pursuing funding from the government also. At this time, I do want to take a minute to acknowledge the people whose hard work actually helped create a lot of the work you saw today. I've co-advised a lot of students. Matt Seberg just graduated. He's at SLAC now. Zeiss scooped up Bosheng in the minute he graduated. That's his little utility belt that we got him when he graduated. Dennis, Liz, Chrissy, Rob, Michael, and Charlie are actually right now working to make some of these ideas a reality. I advised some undergrad and high school students while I was here. Lee Martin is at Berkeley, Carson's at MIT, and Daniel was actually a high school student when he joined. He's at Princeton now, and we were able to get first author papers on this work with all of these students during their time here. We have a lot of collaborators that we're working with to make this a reality, and a lot of different funding agencies. But as I leave off here, I want to kind of put in your mind this idea, this grand challenge that we can do three-dimensional, real-time functional imaging of nanosystems with elemental specificity. So we want to build a microscope that can give us elemental maps in 3D at the wavelength limit with femtosecond temporal resolution and sub-nanometer spatial resolution. So at this time, I'll go ahead and answer any questions that you guys may have.
Thank you, Dan. Dennis, I think you could